So here what we have is a simple, averaging filter. Right? Here the output is equal to the average of the most recent two inputs. Right? So we call this a two-point averaging operation. Okay. Now, what is the impulse response to this system? Right. The impulse response is the response to a unit impulse at the input. Okay. So if you want to get the impulse response, you just plug in x of n equal to delta n, right, the unit impulse, and this is what you get. Okay. So the the impulse response is basically 1/2 at time 0 and 1/2 at time 1. Okay. So then what is the frequency response? All right, so previously we gave a formula for computing the frequency response from the impulse response. Okay, so if you recall, this is the summation of hn e to the minus j omega n for n from minus infinity to infinity. Okay? So hn is non-zero only for two terms, right? N equal to 0 and n equal to 1. Right? At n equal to 0, this is 1/2. So you have 1/2 times e to the 0 is 1. Okay? So when n is 1, you again have 1/2, right? 1/2 times e to the minus j omega times 1, right? So you have 1/2 times e to the minus j omega. Okay? So this is your frequency response. Now you can bring out half of this, right, e to the minus j omega 2, right, outside of the bracket. Then what you have will be e to the j omega over 2 plus e to the minus j omega over 2, when divided by 2 gives you this cosine omega over 2. Okay? So you can sort of change this into this by bringing out this common term outside. All right? So then this, right, if you're looking at a 2 pi range that is from minus pi to pi, then this will be the magnitude, and this will be the phase component. Okay? So for omega within a 2 pi range, the magnitude is just this cosine omega over 2. The phase is minus omega over 2. Okay. So when you plot this out, the magnitude looks something like this, right? So different from the differentiating filter, this filter amplifies the low frequency component and suppresses the high frequency component. Okay? And it causes a linear phase shift, okay, as the frequency varies. Okay. So I'm plotting this only over 1 2 pi range, right? If you look, further down, let's say from pi to 3 pi, then you would just have this same thing repeating over and over again, okay? Because this h is periodic. Right. So you can see here that we have larger attenuation at higher frequencies. Okay. Less attenuation low frequency. Now, these are examples of frequency shaping filters, okay? Now, another class of filters that you often encounter is the class of frequency selective filters, okay? So instead of just trying to shape your spectrum, now we want to be selective in terms of the frequency components that we let through the system, okay? So frequency selective filters are filters that select some bands of frequencies, right? Lets through some bands of frequencies and rejects, other, bands of frequencies, okay? So this is useful in many different applications. For example, in communication, you often may want to cancel noise in some high frequency band that does not fall into the frequency band of your message, okay? So therefore, when you receive a signal, you want to pass it through a frequency selective filter that lets through only the signal of interest, okay? Now, this is also useful when you're trying to extract desired signals from a frequency multiplexed signal, okay? So what is a frequency multiplexed signal? So a frequency multiplexed signal is something like you would see when you're listening to a FM or AM radio, right? So when you adjust to different channels, right, you're basically, tuning your system to listen to the radio station at different frequency bands, okay? So in order to just listen to a single radio channel without interference from other channels, you need to impose a frequency selective filter that lets through the signal only of the radio station that you're interested in and suppresses all the other radio stations, right? Okay. So these are examples of how frequency selective filters may be used in practice. Now, you can roughly categorize them into low pass, high pass, or band pass filters, depending on which frequency band you're letting through. Okay, so for example, a typical low pass filter may look something like this. So a typical low pass filter, right, may have a magnitude frequency response that passes signals in the low frequency component, I suppose this is omega, and lets through signals, suppresses signal in higher frequency components, okay? So the band of frequencies that you let through is called the pass band. Those that you suppress are called the stop band. And the frequency that sets the boundary between the pass band and stop band is called the cutoff frequency. Okay. Now, in practice, when we look at frequency selective filters, right, when we try to design frequency selective filters in practice, we're often concerned with how effective this filter is in the pass band, right? How effective, meaning, how well we maintain the gain over the pass band, or how effective this is the stop band, meaning that how effective are we able to suppress signals in the stop band, and also how fast does this filter transfer from the pass band to the stop band, right? Usually you would need some, non-zero, non-zero frequency range in order to go from pass band smoothly to the stop band. Okay, and all of this, right, is relevant, relative to the ideal frequency selective filter, right, which often assumes that you can perfectly let through signals in the pass band, perfectly stop signals in the stop band and can transfer from one to the other immediately, okay? So an ideal low-pass filter with cutoff frequency omega c will have a frequency response that looks like this, right? It will have a perfect 1, right, in the low-pass band, perfect 0 in the band outside of omega c, and this transition is perfect at, this cutoff frequency, okay? So you can also define similar ideal high-pass and band-pass filters that look like this and this, right? So here, we let through frequencies perfectly above omega c, suppress them perfectly below omega c, okay? Or in the bandpass case, we let through signals perfectly, right, between omega c1 to omega c2, and suppress all signals in other frequency bands, okay? So this is the continuous time case. You can look at these things similarly in the discrete time case, okay? So in discrete time, you can also define these ideal, low pass, high pass, and band pass filters, okay? So why do I say this is, this is high pass and this is band pass? Right. So when you're looking at discrete time filters, you're looking only at the frequency response over a 2 pi range. So suppose we cut this from minus pi up to pi. All right, so suppose we look at the range from minus pi to pi, okay? Then it becomes more clear, right? So then you can see that this is clearly in the baseband, this is in the high frequency band, and this is letting through frequency bands in between, okay? All right. So like I mentioned, this is a low pass. This is high pass. And this is band pass. Okay. Okay. So when we study, these frequency selective filters at first, we often like to start out with these, ideal filters, right? Because it's more easy to handle, okay? But in practice, you can never really realize such a perfect filter, right? You won't be able to realize something that perfectly lets through signals in the pass band, perfectly stops signals in the stop band, and has an abrupt transition, okay? So the closer you get to this, right? If you want to get closer to ideal filter, ideal frequency selective filter, this typically means that you have to increase your hardware complexity tremendously, okay? But if you're not concerned, right, with being so perfect, then this high pass or low pass filter can actually be implemented simply using a simple RC circuit, okay? So for example here, suppose we consider this simple RC circuit in cascade, and we let the input be the voltage source and the output be the voltage across the capacitor. So in this case, the input-output relation can be described by this linear constant coefficient differential equation, okay? So here, VC is the voltage across the capacitor. All right? So we already looked at this system before in previous chapters, and we know that by assuming the condition of initial rest, we can show that this system must be linear and time invariant, okay? So if it is a linear and time invariant, this means that if we plug in a complex exponential at the input, then the output must be the same complex exponential scaled by this frequency response h of j omega. Okay? Now at this point, we haven't yet derived what is this frequency response. Okay? But we know that this must be true. Okay? So we can go on and plug this back into the equation above. Okay? We plug both of these back into the equation above. Okay? So this gives us, RC times the derivative of h of j omega times e to the j omega t plus h of j omega e to the j omega t equal to e to the j omega t. Okay? So I'm plugging in Vs equal to e to the j omega t here. And then I'm plugging Vc, which is h times e to the j omega, inside here and here. Okay? Okay. So then if you work out the derivative, this will give you j omega Rc h of j omega e to the j omega t plus h of j omega e to the j omega t equal e to the j omega t. Okay? Now we can cancel out the common terms, e to the j omega t, right? And then, move the terms around. You can find h of j omega equal to 1 over j omega Rc plus 1. Okay? Now, we're often more used to writing the complex, the imaginary term in the numerator. So I can do that by multiplying both the numerator and denominator by 1 minus j omega Rc. And that will give me 1 minus j omega Rc over 1 plus omega square R square C square. Right, now let's see what this filter looks like, what this frequency response looks like. So we like to express it in terms of the magnitude and the phase, okay? So the magnitude is just the square root of the square of the real part plus the square of the imaginary part, okay? So the magnitude is just the square of the real part plus the square of the imaginary part square root. Okay. Okay. So I'm just taking the square of the real part and the square of the imaginary part, right, with the square root. Okay. So if you work this out, right here you have in the numerator 1 plus omega square R square C square, which cancels out with one of these terms in the denominator. So eventually what you get is 1 over, well, let me write it below. Okay, so this will give you 1 over square root of 1 plus omega square R square C squared. Okay. So then what about the phase? Okay, what about the phase? Okay. So we know that the phase for h of j omega, we can write it as the magnitude and the phase. Right? So by Euler's formula, you can write this as the magnitude times cosine of the phase plus j, the magnitude, times sine of the phase. Okay? So if you divide the imaginary part by the real part, right, what you get is tangent. Right, so suppose that this is the real part, this is the real part, and this is the imaginary part. Okay? So then if you take the imaginary part over the real part, what you get is tangent, the phase of h. Okay? So therefore, if you want to find the phase, you take the ratio between the imaginary and the real part. Okay? So this is omega RC, minus omega RC over 1 plus omega square R square C square over 1 over 1 plus omega square R square C square arctangent of this. Okay? So this phase is arctangent of the imaginary part divided by the real part. Okay? So this term cancels out. Arctangent is an odd function, so I can move the negative sign outside. So this can be written more concisely as minus arctangent of omega RC. So this is what you get eventually, right? So you get a filter with magnitude that looks something like this. Right? You can see you have a peak when omega is equal to 0, and then as omega increases, it starts to decay. Okay? And you have a phase. Okay? We know that if you don't look at the negative sign, right, arctangent converges to pi over 2 as omega goes to infinity, and goes to minus pi over 2 as omega becomes minus infinity. Okay? And this negative sign in the front switches this around. So instead, as omega goes to infinity, this converges to pi over minus pi over 2. And on the other side, it converges to pi over 2 as omega goes to minus infinity. Okay? So this is an example of a non-ideal low-pass filter because we're letting through the frequency, the low frequency components, and trying to suppress high frequency components. Okay. Now this is the frequency response. Now on the right-hand side, what we have is the unit step response, S of t, and the unit impulse response. Okay? So the tau here is actually the constant R times C. Okay. All right? So on the right here, we have the step response, where you get S of t equal to 1 minus e to the minus t over RC times u of t. Okay? And you can obtain this step response by plugging in the unit step function as the input and solving the differential equation under the condition of initial rest. Okay? And then if you take the derivative of this, you get the impulse response above. Okay. Now the reason I want to show this both in the frequency domain and in the time domain is because through these figures, you can sort of see a trade-off in the time and frequency domain, right? So in the frequency domain, you can see that this low-pass filter here has a passband that is roughly determined by 1 over RC. So the larger is RC, the narrower will be your low-pass filter, okay? But as RC increases, this tau increases, okay? So this means that your impulse response will be decaying slower, okay? So in order to have a narrower, right, or a more specific low-pass filter, you would have to, deal with a response that is slower in the time domain, okay? And often you need to strike a, balance between the two, depending on, which part is more important for your application, okay? All right. Now, I don't want to go into the details of this next example, but this next example is just to show that you can, construct a similar high-pass filter in a similar way by just looking at the voltage across the resistor as the output instead of the voltage across the capacitor, right? So if you instead look at this voltage as the output, then what you have is actually a system with a response that looks like this, right? So it passes through frequency components in a high pass band and suppresses the low frequency components, okay? So here, VRT is the voltage across the resistor, okay? And you could have obtained this directly by the fact that, VST should be equal to VR plus VC. Okay? So, this voltage across the source should be equal to the voltage across the resistor plus the voltage across the capacitor. Okay? So, by plugging VC as Vs minus Vr into this equation here, you can directly obtain this differential equation. Okay, and then, by the same approach, you will be able to find its frequency response. Okay, so this gives you a high pass instead of a low pass filter. Okay. All right, so here I have one more example. The insights are more or less the same, but this is just to give one more example of the case in discrete time, okay? So here the system we're looking at is described by this difference equation, yn minus a, yn minus 1 equal to the input xn, okay? So again, by the eigenfunction property, we know that if we plug in a complex exponential at the input, the output should be the same complex exponential scaled by this frequency response h. Okay. So then if I take this, plug it back inside, I should be able to obtain an expression for the frequency response. Okay. So if I plug this inside, I get h e to the j omega e to the j omega n minus a h e to the j omega times e to the j omega n minus 1 equal to e to the j omega n. Okay? So if you cancel out the common terms, e to the j omega n, right? And by moving the terms around, eventually you can solve for solve for the frequency response to get 1 over 1 minus a times e to the minus j omega. Okay. All right. So to see if this is a low pass or a high pass filter, right? We're mostly concerned with the magnitude of the response. Okay. So the magnitude, the absolute of h okay, the absolute of h of e to the j omega, I can compute by taking 1 minus a e to the minus j omega times its complex conjugate, which is 1 minus a e to the j omega absolute square. Okay? All right. So you just have to work this out, right? So here you have 1 times 1, which is 1. You have a e to the minus j omega times a e to the j omega, which gives you a square. And then you have this term times 1 plus this term times 1. And by Euler's formula, this gives you a cosine. Okay? So this overall gives you 1 plus a squared minus 2a cosine omega, okay, 1 over square root of this. Now, whether or not this is a low pass or high pass really depends on whether a is positive or negative. All right. So if assuming a is positive, okay, assuming a is positive, and that we're looking at omega over a 2 pi range from minus pi to pi, then as omega increases, okay, let's see, as omega increases from 0 to pi, okay, as omega increases from 0 to pi, this cosine becomes smaller and smaller, okay? Cosine smaller means that the denominator becomes larger, and therefore 1 over the denominator becomes smaller, okay? So when a is greater, the gain attenuates. So for a greater than 0, the gain attenuates as omega increases. Okay? And this is vice versa when a is negative. Okay? So for a less than 0, the gain instead peaks as omega increases to pi. Okay? And you can visualize this by plotting this out. Okay, so if you plot this out, you will get a figure like this when a is greater than 0. Okay, and you can see that this is somewhat of a low-pass filter. And when a is less than 0, right, you see that the gain peaks as the frequency increases up to pi, okay? And therefore, this is a high-pass filter.